This video is I'm going to explain the trig substitution technique. It's a technique that's maybe one of the more challenging techniques, but it is used to deal with unruly square roots, and sometimes you can deal with a square root by using trig substitution. I'm sorry, but regular U substitution. But sometimes that won't cut it, and so we look for situations like this one here, like number 1, where you can see that in order to use normal U substitution, we'd have to have a little x on the outside or something, so that we can deal with the derivative of the inside there. But we don't, so we need some other technique. And so here's a little helpful reminder for trig substitution. The idea is if you see an expression like this, then you want to, basically they're telling you what kind of U substitution to do. But then they say you want to substitute x equals a sine theta. And if it looks like this, then you want to substitute x equals a tangent theta. And if it looks like that, or something like that, then you want to use a secant theta. So that's the idea. And so when we look at this, we see it's a constant minus x squared, and inside a square root. And so if you look over here, it's that first one we circled, isn't it? So that gives me the hint that I should use the x equals a. So in this case, that would be 2 sine theta. Okay, again, everyone see where the a comes from. So you could rewrite this as the integral of the square root of 2 squared minus x squared dx, and then you can see that the 2 is a, and that's where I got the 2 from. So we're letting x equal 2 sine theta, which means dx, because we always have to figure that out whenever we do substitution, right? So dx would be 2 cosine theta d theta. Okay, so far so good. So now we're going to make our substitution. So when we make our substitution, we get the integral of the square root of, this is 4, minus, of course we don't do anything with the 4, x squared becomes 4 sine squared theta, and the dx becomes 2 cosine theta d theta. Okay, so now here's the reason why we picked this, and why it works out nicely is because we know that we know this trig identity right here, sine squared plus cosine squared equals 1, which we're more interested in this form, 1 minus sine squared is equal to cosine squared. So we can rewrite this integral as the integral of, and we can factor out the 4, so that would be the integral of, the square root of 4 times 1 minus sine squared theta times 2 cosine theta d theta. And if we keep going, the 4 will factor out, leaving it, it'll just be a 2 times 2 is 4. So the square root of 4 is 2, and then times 2 would be 4. And then this becomes the square root of, and 1 minus sine squared is just cosine squared. And then we have a cosine theta d theta. Okay, so then that would be the integral. Of course, cosine squared square root is just cosine. So we get 4 cosine squared theta d theta. So now we're ready to, well, we're probably not quite ready to integrate this because there's a cosine squared there. If it's just cosine, it'd be easy to integrate to sine. This cosine squared is a problem, so we're going to have to dig back into our good old trig days and remember the cosine 2 theta is equal to 2 cosine squared minus 1. That was the double angle formula from your trig A's. If you can look that up if you forgot it. But now this what we're gonna do is solve this so we can get cosine squared by itself. So that would be cosine 2 theta is equal to 2 cosine squared theta. Divide both sides by 2. Whoops, I didn't add the 1 over there. Plus 1 is equal to cosine squared. 2 cosine squared. Then divide everything by 2, so we get 1/2 times cosine 2 theta plus 1 is equal to cosine squared theta. Okay, so then to solve this, we'll rewrite that as, well, that 1/2 will come out front and blend in with a 4, so it's just a 2. So in the integral of cosine 2 theta plus 1 d theta. And now we can integrate that. That would be, that comes from sine of 2 theta. And the derivative of sine of 2 theta would be cosine 2 theta times 2. And there's a 2 out there, so that's perfect. And then this would be plus theta and plus c. But of course we can't leave it as plus theta and plus c. I'm sorry, we can't leave it as theta. We need to get it back in terms of x. So now this is where trig substitution gets a little bit tricky. So we're going to back up a second here and make what we call the reference triangle. So when we made this little substitution over here, we said that x is equal to 2 sine theta. So if we put a little theta there, divide both sides by 2, we get x over 2 is equal to sine theta. So that means that, and remember sine is opposite over hypotenuse, so that means we could call this x and this 2. Which means this other side here would, using Pythagorean theorem, would be the square root of 4 minus x squared. And notice that's exactly that phrase that we got in there. So that, and that's the way these things usually work out. So, and then from this, of course, we can define all the trig functions. We can define sine of theta, which we already know, but we also can, which is x over 2, but we can also define cosine of theta, which is the square root of 4 minus x squared over 2. We could do tangent and cosine, etc., because we know what the triangle looks like in terms of theta, and we know how the different trig functions are assigned based on that triangle. Okay, however, the problem is we don't know what sine 2 theta is, so we're going to use another trig identity. This will, there's a trig identity that says sine of 2 theta is equal to 2 sine theta cosine theta. So this will become 2 sine theta cosine theta plus theta plus c. So then we're going to make a substitution for sine theta. So this is going to be 2 times, of course, sine of theta is x over 2. And cosine theta, we just said, is the square root of 4 minus x squared over 2. And finally, theta. Well, theta, if we wanted to, we could take the inverse sine over here and find out what theta is. So that's going to be arc sine of x over 2. And then plus c. And we can simplify this. Those 2's will cancel out, so I'm left with an x times the square root of 4 minus x squared all over 2 plus arc sine of x over 2 plus c. So about that x at 2 is not very pretty. Okay? Now I just realized that I forgot something here. There's a 2 sitting out here that I didn't account for. So that 2 should have been sitting right there and right there, which would have made it this 4 and this 2, which would have made that 4. And both the 2's would have canceled out, so we wouldn't have that 2 there. And that 2 would have just flowed along right there. Alright, so that's your first run at the trig trig substitution. So we're going to do the same thing on this one. I'm going to blow it up a little bit so it's a little bit, so I can fit it in better. So it's 9 plus x squared. So if we go over here and look at this, that looks like that guy right there, doesn't it? Because 9 is 3 squared. So it looks like we want to use x equals 3 tangent theta. Okay, so I'm going to go over here. Maybe I'll make a little room here. So if we let x equal 3 tangent theta, that means that dx is equal to 3 secant squared x, I'm sorry, theta d theta. And so my integral is going to be, the dx will be replaced with that, so I'll have a 3 secant squared theta d theta on top. And on the bottom, I'm going to have the square root of 9 plus 9 tangent squared theta. Okay, so of course we can simplify some stuff here, and we get the integral of 3 secant squared theta d theta on top, and on the bottom we have a square root of 9 times 1 plus tangent squared theta. And of course, if you know your trig identities, you know that 1 plus tangent squared theta is secant squared. So this is going to be the integral of, and of course the square root of 9 is 3, so those will cancel out. So I'll be left with a secant squared theta d theta on top, and a tangent, or sorry, and a secant squared theta with the square root on it. So, of course, that secant squared square root is just going to be a secant, so we end up in the end with just a square root, an integral of secant theta d theta. So that was a lot of work, and but it did change it quite a bit, didn't it? So it makes it look a lot simpler. So this one is also another tricky one. So the trick here, which again, I know some of you are going to say, when would I ever think to do this? You change this to the integral of secant theta times secant theta plus tangent theta over secant theta plus tangent theta, which of course we're just multiplying by 1, so it doesn't change anything. So then when we do that, we get the integral of secant squared theta plus secant theta tangent theta all over secant theta plus tangent theta d theta. Now, why would we want to do that? That seems like a crazy thing, but if you look closely, you realize that the top now is the derivative of the bottom, because the derivative of tangent is secant squared, and the derivative of secant is secant tangent. So then this just becomes the natural log of, well, okay, I guess I better do a little u substitution here, so you can see it. So if you let u equal secant theta plus tangent theta, then du is going to be secant theta tangent theta plus secant squared theta d theta. So this integral becomes du over u exactly, and that would just be natural log of u, which remember is secant theta plus tangent theta. All right, so that is my integral, but once again we've got to change it back to x's, so we're going to go back up here and look at our original substitution. We find out that x over 3 is equal to tangent theta, tangent theta. So let's go back down here. We'll draw a little rectangle over, or a triangle, I mean. So if we got a triangle, here's my theta. Tangent is opposite over adjacent, so that'd be x over 3, which means this would be the square root of x squared plus 9, which again, notice that's the same thing that was in our original integral, x squared plus 9, square root, yep. So that means that the natural log, secant, so remember secant is, well, cosine of theta would be adjacent over hypotenuse. So secant of theta would be that flipped over. So this would be the square root of x squared plus 9 over 3. And then tangent, of course, is just x over 3, as we said earlier. I'm going to put a plus c there. So you can see these trig substitution ones are dandies. So let's, we'll keep working at this and see what we come up with. Let me see if I can find one that's a little bit nicer. That actually looks like a decent one there. So this is 1 minus 9x squared, which doesn't really look like any of these. Of course, closest to that one, right? But that's a little bit troublesome to see what a is, because it's not 1. So what we're going to do here is we're going to change this to the integral of 1 dx, and we're going to divide out a 9. So that means if we divide everything by 9, we're going to have this square root of 9 times 1/9 minus x squared. So we can see what the a is. So if we clean this up a little bit, that 3, that square root of 9 is 3. So I'm going to put him outside so I don't have to worry about him. I'll have a dx on top, and on the bottom I'm going to have the square root of 1/9 minus x squared. So now we can see what the a is. It'd be 1/3. So we want x to be equal to 1/3 sine theta. Because remember that little box tells us if it's a perfect square minus x squared, we want to use sine theta, right? So then, of course, my dx will be equal to 1/3 cosine theta, d theta. And we're going to come down here and make the substitution. So we have the 1/3, the integral of, and the dx will be replaced with 1/3, so I'll put a 1/9 out front. And that's going to be cosine theta d theta. And on the bottom, I'm going to have the square root of 1/9 minus 1/9 sine squared theta. Okay, so then it's kind of, you can see there's kind of a similar pattern to all of these. So we're going to have a cosine theta on top. On the bottom, you're going to factor out a 1/9, which when we take it out of the square root will be a 1/3. And inside the square root, we're going to have 1 minus sine squared theta, which of course 1 minus sine squared theta is cosine squared. And let's bring that 1/3 out. 1/9 divided by 1/3. So this 1/3 is actually going to be multiplied by 3. So that would be 1/3 the integral of cosine theta d theta over the square root of cosine squared would just be cosine theta. Now look at that. So this is just going to be 1/3 the integral of, and cosines cancel out, d theta. Wow, you couldn't ask for an easier one than that. So the integral of this is going to be 1/3 theta plus c. Now, what's theta? Well, remember, if we take this guy right here and solve it, that'd be x over, or excuse me, that would be 3x is equal to sine theta. So then arc sine of 3x would be equal to theta. So this is just going to be 1/3 arc sine 3x plus c. Okay, so there's 3 examples of trig substitution, and I would encourage you to try your hand at them. I just posted a worksheet with some trig substitution examples on there, and on the canvas. So, and I will be making some more videos of me working through some more of these problems, because these definitely are challenging. So, thank you.